Is that clear? Yeah. So, but after sampling, after this sampling, so let me actually copy this figure. Let me try to copy this figure. Let's say we have a high frequency signal in time, in continuous time. And we sample it with a rather long period. If we sample that signal with a rather long period, what we get might be, let's say, let me just try to say 1T, 2T, 3T, 4T, 5, 6, 7, 8, 9, 10, and so on. Okay? So that's the result after sampling. I'm going to mark them with circles. Right. Actually, this is not a very good example. Let me further increase my sampling period. Yeah. But anyway, so I want to show you that if you just now pretend that you are not seeing the red line, okay? Pretend that we are only looking at the samples. Yeah. So probably by looking at the samples, you might construct a continuous time signal that passes through all the samples, but it is different from the red one. Yeah. So what I'm trying to say is that if we just look at the samples, then your brain might interpret the signal as something like that, which is different from the original one. Okay? So that being said, I'm telling you this is an example that the original signal and the signal that I reconstruct are different, of course, but they will result in the same sequence after sampling. Therefore, sampling, the operation of trying to sampling a signal is not invertible because we have a 2-to-1 mapping. A 2-to-1 mapping is not invertible. Okay? So generally, the answer is no. C to D conversion is generally not invertible because of what we call aliasing. Okay? Two signals can become identical after sampling. In that, they become identical. Okay? They happen to equal at n times multiple of t, where n are all integers. It could happen. Theoretically, it could happen. So therefore, it's generally impossible to exactly determine x of t from its sample, from its discrete samples x of n. Generally, it's impossible to uniquely determine the analog signal after the analog signal is sampled. So but it's well known that here, if we add a constraint, if we add a condition, okay? So, however, if we say that the signal is band limited to begin with, or in other words, when we say band limited, that means if the bandwidth of your continuous time signal, if the bandwidth is finite, is limited, okay? To begin with, then it becomes possible to reconstruct your signal from its samples. Yeah. And roughly speaking, this is a famous sampling theorem, just a Nyquist sampling theorem, which states that, roughly speaking, as long as your sampling frequency is higher than the 2 times of bandwidth, if we sample with a sufficiently high frequency, and where sampling frequency is defined by 1 over t, okay? T is the sampling period. So sampling frequency tells you how many times we look at the signal per unit time, okay? per second. Yeah. So the sampling frequency, it turns out that if the sampling frequency is at least 2 times the bandwidth or higher, the higher the better, okay? As long as the sampling frequency is more than 2 times higher than the bandwidth of your signal, then turns out that there's a way to reconstruct the continuous time. Okay? Then the reconstruction becomes possible, and we call that reconstruction D to C conversion. So now D to C to D becomes the invertible with D to C. So I just say, in general, in the most general sense, if you attempt to, when you attempt to create, so in the most general case, because of aliasing, the reconstruction is going to be different from, could be different from your original signal. But what if, if your sampling frequency, 1 over t, is greater than at least 2 times the bandwidth, b being the bandwidth of your continuous time signal, then this reconstruction, the 重建 reconstruction becomes possible. And we'll explain that next. So to explain that, we need to define what do we mean bandwidth. Okay? We haven't officially defined that. So here is a discussion I want to cover for today. So we'll need to introduce the Fourier transform. Okay, so let's still keep that figure here. Let's say now we have a signal. Okay, we have a signal x of t, and first let's take a look of this definition. So we define the Fourier transform of your signal by performing that integral. Okay, so we're going to take your signal and then multiply it with e to the minus j big omega t, and then we take the integral from minus infinity to infinity. The result being the Fourier transform of your signal. Okay, and also let me also mention that in this course we are going to denote the result by capital letter. Okay? In this course, we are going to consistently use lowercase for time, capital big X for frequency. Okay? So after going to the frequency domain, the result is going to be denoted as a spectrum, which is a function of omega. Okay? Omega being the frequency. So that's a definition of the continuous time Fourier transform. And now, let's consider what's going on when we sample the signal. Okay? So when we sample the signal, we're going to, we look at the signal every integer multiple of a sampling period. Okay? And so here we want to introduce this function called s of t, right? So here, I claim to you that when we sample a signal, it is like we are multiplying our signal with s of t. And what is s of t? S of t is an infinite sum of Dirac delta functions located at integer multiple of t. Right? So we draw a sketch of s of t. It's pretty easy. We draw a sketch of s of t. It's just a delta function at time 0, right? And shifted by t, another delta function at time t, another one at 2t, and every one at integer multiple of t. Okay, so that's S of t. And the summation just goes indefinitely in time, still in continuous time, just conceptually. So let's define, just utilize this S of t. And now I invite you to consider what's going on when we multiply S with your continuous time signal. What will happen when we multiply this S of t, all equaling height? Okay? This height is 1, just because S of t is that, right? S of t, where S of t is simply an infinite sum of delta function located at n times the sampling period. N from minus infinity to infinity. I'm saying that the height is all equal. Just a unit height of the delta function. So I want to invite you to consider what will happen when we multiply a continuous time signal with S of t. Okay? When we multiply that, so let me claim that the result is going to become summation still. The result is going to become the result becomes this. The result becomes that every delta function now, their height is modulated by your signal. Can we agree on that? When we multiply this sequence of impulses with a continuous time signal, the result is a sequence of impulses, but the heights are modulated by that signal. Yeah? The heights are modulated, are adjusted according to that signal. Okay? So we just, if you are with me, if we write down the result of this multiplication, the result is going to be a sum of infinite sum of all the impulses located at t at n times the sampling period, but their heights are modulated by our signal also at n times the sampling period. Is that clear? This is just by drawing. Yeah, so you can process this in your head. Okay, this is correct. But then, what is this? What is that term? That term is your discrete time signal, right? Yeah. So this further equals to summation over all n, x of n, delta t minus nt. So when I write summation over n, so I'm being lazy here. I hope it is fine. I'm being lazy, 懒惰. So I'm being sloppy. When I don't mention the summation index, the range, that means sum over all n. Sum from minus infinity to infinity. Okay? Yeah. So this is one way to look at what's happening when we multiply our continuous sine signal with a sequence of direct impulses defined as such. Right? The result is basically sampling. Yeah. We can say that this is a way to write down what's going on after sampling. Right? After sampling, we have a sequence of impulses, and each adjusted with the height of that continuous time signal. That's what's going on. That is sampling. Right? Sampling is to multiply your signal with S. Is that clear? Equivalently. You can think of this as an equivalent. What's going on in time when we sample a signal? In the time domain, we multiply our signal with S. Any signal, when you sample in time, first of all, you tell me the sampling period, and then the operation of sampling can be written down as if we are multiplying our signal with S. Is that clear? Sampling is to multiply with S. So if we are with me so far, then let's move on a few steps further. if sampling is multiplying your signal with S, then let's say we have a signal, any signal again, and we sample by multiplying with S. So this is sampling. Where S is defined as summation of over all n delta of t minus n times the sampling period. Okay, nothing's new so far. But then I want to introduce to you something that's rather new. Okay, something that's quite new. Oh, by the way, if I haven't mentioned, in this course we use J to represent the square root of -1. We use the letter J, right? And also e to the J something means cosine that thing times plus J sine that thing, right? So but now I want to show you one new thing right here, okay? Let's take a look. So after defining that Fourier transform, it turns out that you can consider the Fourier transform of S. Okay? The Fourier transform of S, and this is S. Turns out that, or should I say, let me just introduce this, right? Let me just introduce this. S of t. S of t can be written as a Fourier series. So this is one new thing I want to introduce to you. Okay? S of t, on one hand, is defined as a sequence of Dirac impulses. So that's one way to write down S of t. But it turns out that S of t can be also expressed as its Fourier series expansion. This is the Fourier series expansion for S of t. Okay? Turns out that S of t can also be written as 1 over p. That's not that important. But the important thing is that now we have a summation of complex exponentials of e exponential j times what? There's a summation index over all k, about the k and 2 pi divided by sampling period t. And let me just give a remark. This is Fourier series expansion. So this is Fourier series expansion, and the reason why we can perform this replacement, the reason why this equality holds, we are not going to tell you all the details, but we will come back to this in a FUD session, right? So 2 weeks from now, we are going to officially discuss what's going on right here. But let me just try to convince you that if you agree with me, S of t, by definition, is a sequence of delta impulses, and it's a periodic signal, right? Any periodic signal can be, we can perform Fourier series expansion. And this is it's the result of Fourier series expansion. The result is what? Is a sum of periodic signals at k times the fundamental frequency. Okay, so here note that 2 pi divided by t is the fundamental frequency. So this is the equality that we are going to use next. Okay, so if we perform Fourier series expansion of S of t right here, then some magic can happen. Okay, then still, X sampling is to multiply our signal But now, instead of writing it as a summation in time, we write it as a summation of harmonics in the Fourier series. Okay, so then still 1 over t right here. I'm going to copy everything. I'm going to copy everything s of t inside the bracket. Okay, so 1 over t summation over all k exponential j k times 2 pi times the fundamental frequency, still t is there. So that's the result, right? One step further. So that's one step further. So far, so good? One step further. So guess what? What I'm going to do next? What I'm going to do next is to put our signal inside the summation. And I can do that because summation is with k, right? So let's put x of t inside the summation. So now, going one step further, 1 over t is still there, summation is here over all k, all possible integer k. But now inside the summation, we have our original signal multiplied with exp j k 2 pi divided by t, the fundamental frequency times t, and the summation, like that. Now we are putting our signal inside the summation. Okay? So when we put the signal inside the summation, the next step now finally is to consider the Fourier transform. Okay? So from there, let's go back to the screen. Okay? So now let's take a look. We are performing when you, now after multiplying, or after sampling, which means to multiply with s. After sampling, and we know the result of sampling is this, right? But now when we take the Fourier transform, when we attempt to go to the frequency domain, that's the next thing we want to consider, okay? So next, let's consider going to the frequency domain. Let's consider going to the frequency domain, okay? So if we consider going to the frequency domain, we know that Fourier transform is linear. So quickly, we can put Fourier transform all the way inside the summation. And that's what's going on right here. That's what's happening now in the frequency domain when we sample the signal by multiplying with s. Let me summarize our observation right now, okay? So we sample our signal in this picture. And soon we realize that to sample means to multiply with s in time. Okay? And it turns out that s can be represented using its Fourier series expansion in here. So therefore, when we now finally consider what's going on in the frequency domain, the result is 1 over t, a summation. The Fourier transform moves inside the summation, like that. Okay? But now, if you agree with me on so far, then what is this? When we, now in here, we really focus on this term inside the summation. When we multiply our signal with complex exponential of fixed frequency right here, there is a shift theorem in Fourier transform. That means that when you modulate a signal with this complex exponential term, the result is, and then consider the spectrum. The result is the spectrum shifted by k times that frequency. I should say the result of multiplying a signal with exponential j omega t is a shift in the frequency domain. That's the shift theorem applied right here. Okay, right here. Multiplying your signal with e to the j big omega t, and then after taking Fourier transform, the result is the spectrum, is that spectrum, but shifted by so much, where I'm just denoting 2 pi over t by this big omega s. So mathematically, now we have an identity, okay? We have an identity. What's going on right here? We have an identity that, let's say, if we denote the result after sampling as that, okay? And then when we take the Fourier transform, taking the Fourier transform, the result is denoted by big X after sampling, and the result is a spectrum, a function of big omega. Okay? So here I'm showing an identity. After sampling, the resulting spectrum has this final expression. It's a final expression. That means that, so when you take a look, the resulting spectrum is going to be the original spectrum, but shifted and superposed. Up here, there's a summation index k right here. So we're going to shift. What's happening in sampling is that in the frequency domain, the spectrum is going to be shifted to the left and to the right indefinitely, summing over all k. Shifted to the right, shifted to the left, and then they all add up. They all sum. They're all summed into the to form the superposed to form the final spectrum. That's what's going on in the frequency domain when we sample a signal in the time domain. So these are the few steps that you need to digest. Okay. So this is very, very important identity. So with that, should I say, let me just copy this right here. So if we take the Fourier transform of sampling, this is sampling after sampling in time. The result is, let me just do a copy. Still 1 over t, that's not very important, but the summation is important. We have a summation over k, okay, and your spectrum is shifted by k times, let me just say 2 pi over t. Yeah. So this is the result that we're going to use. In the next slide, I want to, let's work this out. We are going to do a sketch of what's going on in the frequency domain. Okay? We're going to do a sketch, horizontal. I'll do a sketch of what's going on in this frequency domain. Right? What do we mean? Shifting the spectrum and then add them all up into a summation. All right? So next is to make a sketch, right? Let's make a sketch of that equation. That's equation number 3. All right. Equation number 3. Let's make a sketch. So I guess I'm going to erase the definition of Fourier transform. And I'm going to erase these definitions. But we keep this, okay? Right, so let's do a sketch. What do we mean shifting the spectrum and then perform a summation like that? Here's my white one. Okay, so probably easier to go back. Take a look. Yeah, that's the equation right there. So let's say this signal, when it goes to the frequency domain, it becomes a spectrum. Okay? Let's say our spectrum has this very basic shape like that, okay? With a bandwidth of something. So this is what we mean bandwidth. Let's say this is frequency B in the frequency domain, right? Suppose that this is our spectrum, the spectrum of our signal, okay, which is illustrated by a triangle right there, okay? So that's before sampling. But after sampling, we already know that the result is going to be the spectrum shifted but superposed. Shifted and superposed. So let's say now to the spectrum right here, and then it's shifted by omega s. So now there's another copy centered around the sampling frequency. But then that summation goes indefinitely, right? It goes indefinitely. So we have yet another copy that's centered around 2 times omega s, right there. Same thing. And similarly on the negative frequency side. So just for illustration, we can say that after sampling, the resulting spectrum is the original spectrum. But now we have indefinitely infinitely many copies of the spectrum, but centered around integer multiples of the sampling frequency. Okay? Sampling frequency being 2 pi divided by t. So that's what's going on when we sample the signal with this sampling frequency. But the next thing is, so in this example, the sampling frequency is larger than, in this example, the sampling frequency clearly is larger than 2 times the bandwidth. So there's separation. There's separation. I mean, different copies do not interfere with one another. There's no interference. Okay? But what if, now, in another scenario, what if we lower the sampling frequency? When we lower the sampling frequency, let's say if now the sampling frequency is reduced to this new one. Okay? Now, if this is the sampling frequency, then after sampling, as we said, because of that equation right there, we have another copy of the spectrum that's centered around this lower the sampling frequency, as well as 2 times that, 2 times that, and so on and so forth. And let me also draw one at the negative frequency side. So we have another copy of the spectrum shifted to the left by so much, and so on indefinitely. So now the resulting spectrum, after sampling, now the resulting spectrum may look like that. Right? Now the resulting spectrum may look like that as an illustration. And this is the exact reason why we don't like it. We don't like it when the sampling frequency is no more than 2 times bandwidth. We don't like it when the sampling frequency is less than 2 times the bandwidth. Why? Because now the resulting spectrum is distorted. Now this resulting spectrum is no longer a perfect triangle. The shape has changed. Okay? The shape has changed, and we don't like it. Okay? Different frequencies. I mean, this is high frequency, but it's going to be, this high frequency component is going to be superposed with low frequency component, and they add up. Some high frequency component is going to show up at the wrong place, and they will interfere with the low frequency component that's already there. So this interference is called aliasing, showing up at the wrong place, having an alias, okay? Showing up at the wrong place in the frequency domain, and we don't like it. And why do we have it? In this case, we have it merely because the sampling rate is not high enough. Sampling rate is lower than 2 times the bandwidth. Therefore, after sampling, after shifting the copy, there is interference. There are some components that show up at the wrong place in the frequency domain, in the spectrum. We don't like it. But in the meanwhile, so on the other hand, if the sampling frequency is high enough, if the sampling frequency is greater than 2 times the bandwidth, then we have a margin like that, right? So even if we shift the spectrum and make copies, these different components do not interfere with one another. There's a margin. So there's no worry, even though there are extra components. Okay? So later, a few weeks from now, we will explain, this is all right, because to retrieve the original spectrum, we can just apply a low-pass filter. Then the original triangle is retrieved. We got back that triangle. Okay? We can try to reject every extra copies by applying a low-pass filter. That can be done. Conceptually, that can be done. Okay? But in this case, even if you apply a low-pass filter, the result is distorted already. So we don't like it. So that's kind of the spirit of Shannon's sampling theorem, which I summarize in here. Should I summarize in here? Okay. So this theorem can be found. You can find it, Nyquist-Shannon theorem, on page right here from the textbook, which tells us that now, officially, suppose that we define Fourier transform, and we denote the Fourier transform by big X. Okay? Suppose that the Fourier transform of X is big X, and suppose that the bandwidth is finite. The way you write it, look, suppose that there exists a finite bandwidth such that the spectrum is all zero beyond the bandwidth. Is that clear? Let's take a closer look. Let me read that again. If this is spectrum, and suppose that there is a finite frequency, less than infinity, okay? Suppose there is a finite frequency right there, such that all your spectrum is zero beyond that frequency, beyond plus or minus that frequency. So that's a notion of bandwidth. This is 频宽的意思. Suppose your bandwidth is less than that. Suppose so that means suppose that in your signal, everything beyond the frequency is zero. Suppose there is a finite bandwidth of your signal, then what? Then we say your signal can be uniquely determined by its samples. If your sampling rate is greater than 2 times the bandwidth. Right, let me read that. Let's read this together. Suppose that we have a signal and its spectrum, and suppose that there is a finite frequency such that your spectrum is all zero beyond the frequency. That means suppose that your bandwidth is finite, then what? Then your signal can be uniquely determined by its samples. And that's how we mean sampling a signal. It can be uniquely determined as long as your sampling frequency is sufficiently high. How high? More than 2 times the bandwidth. Okay? That's this scenario. We sample at a high enough frequency, then this shift is far enough, so there's no interference. Okay? And just somewhat in kind of mathematical words, this is the way we say it. So that's the sampling theorem. So anyways, it's desired that your sampling rate, you sample at 2 times the bandwidth or higher. Okay? That's kind of take-home lesson. And a remark, we will discuss how to uniquely determine XC, right? And to uniquely determine XC from the samples, that basically means to convert from discrete time back to continuous time. Maybe using a low-pass filter, just maybe. Okay? It can be done. But the word unique is important because, why? Because recall what the question we were asking. I was asking a question, right? We were asking one very question, the very question, whether or not something is invertible. We were asking whether or not sampling, the operation of sampling is invertible. Can we go back to the continuous time? And my answer was no, right? My answer said that no, because we have aliasing. But now, if we sample at a high enough frequency, the answer becomes yes. If we sample at high enough frequency, then we can uniquely get back the original signal. The answer becomes yes. So that's a miracle. As long as we sample at a high enough, with a high enough sampling frequency, at least 2 times. Okay. So, but how exactly to to get back XC, maybe by low-pass filtering. We'll talk about that later, okay, in about 2 weeks. All right, so that's pretty much I want to talk about for the first lecture. That's almost the end. We do have some final remark. We'll get back to that tomorrow. Okay, yeah. That's it.